Hello everybody, so I've been away sick for a few days with a temperature, so I apologize that I've not uploaded anything recently. I've also had some technological difficulties, such as the internet no longer working. So I'm going to record this and hopefully I can upload it when I get back to work. So let's get back into our video series. Now this is a slide of some kind that I made a while back, so it doesn't exactly fit with the number scheme of my current videos lately, but it does fit in topically right after you've passed through electron configurations. So we're going to start look at the assembly of our modern or common periodic table. In the early days of chemistry, they just simply listed all the known elements of their time, and they attempted to organize them as best they could, but as you know, early days they didn't know many elements, so didn't have much to work with. So for example, this guy here is Antoine Lavoisier, French guy. He started putting together the known elements, and he's grouped them as best as he can into different types, but there's not really much to it. Then following on from there, John Dalton attempted to assign some sort of symbolic notation to these elements, which are pretty cool, but again, it's not really a organized table of any kind that's not like what we see today. And if you follow on with other future scientists, they as we knew more about new elements and also more about the chemistry behind those elements, we got better and better at organizing them. So we're going to take a look at this word periodic. Now, it occurred to me some years of teaching this subject that not everybody understood why we call it the periodic table of elements. And that's because it comes from the word periodic, which means to have a repeating cycle. But you might be asking yourself, what exactly is repeating in the periodic table? Well, to illustrate what's happening here, I've just listed all the elements from atomic number 1 up to atomic number 20. In the early days, when they tried to organize their elements, they did them according to atomic mass. However, there were some discrepancies, which I'm sure some of you have already found in your assignments. But when you put them in atomic number, increasing atomic number, things become quite apparent. So here's the first 20. If we start color coding them for similar elements, so for example, I've got all the green ones are the noble gases, or the yellow ones are the alkali metals, the blue ones are alkaline earth metals, and the red ones are the halogens. And if we look closely, we can see that they are appearing at regular intervals from each other when we go left to right in terms of the atomic number. And this interval, at least for the start of the periodic table elements, up to number 20, it appears to be repeating itself every 8 elements, or 8 atomic numbers. So what if we cut that line into 2 rows, such that we could line them up underneath each other, such that the similar elements lie underneath each other in these nice little columns. And I think you can already start to see that as we continue to work with this, we can neaten this up. So for example, this I could cut it out and put helium with its group. Hydrogen has always been a debated element. It doesn't really fit terribly well in a particular group. So group 1, it sort of behaves a bit like them, but it's not really a metal. It also somewhat behaves a bit like a halogen, but again, it's still not a perfect fit. And obviously potassium and calcium can fit nicely underneath these two. So once we do that, it's starting to look a lot more common, like the one we see every day. Now, this is only the first 20 elements. If you start adding the rest, so if I just go to the next bit of the slide, here you can see right in the middle, I've started to include the D block elements, or the transition metals, scandium through to zinc. And now we're starting to see a lot more of this structure that everybody's familiar with. And lo and behold, we keep going. This is the shape we get. So the periodic table gets its name from the periodicity or cyclic nature of its chemical properties in increments of atomic number. That is, the periodicity, the repeating chemical nature of these elements, is a function of their atomic number. Okay, and I've got brackets here. The chemical properties repeat every so often as you increase the atomic number. So what do all these elements have in common with it? So what do all these elements that are similar to each other have in common? Is there some underlying structure to them that brings out these very similar chemical properties. So when we saw a few slides up ahead where color-coded, all the alkali metals, they all behave similar to each other. They all react violently with water. They're all metal. They're usually soft, and they're usually very reactive. What is it about them that makes them so? It turns out it comes down to its electronic structure, or electron configurations. This is part of the reason why I made all of you, my lovely students, draw these, so many, all over on that worksheet just last week. So here I've drawn just group 1, the alkali metals, and you can see hydrogen has 1 electron in its outside shell, lithium has 1 electron in its outside shell, sodium also has 1 electron in its outside shell, and potassium also has 1 electron on its outside shell. That is the thing that is common to all of them. And so this coincidence appears in all of the groups. So you would see the same electron configuration, that is, how many electrons are in the outside shell, or a valence shell. They all have that in common for the halogens, and that noble gases all share a similar electron configuration to each other. It's quite remarkable when you see it. So, and that's it. So this one here is a really bad snippet of the worksheet. It's not really formatted very well, but you've all seen this in my class. For those of you who are viewing on the web, I might see if I can find a way of putting it up online for you to fill in, but I'm sure you can get the point. If I can't find a way of putting it up for copyright reasons, essentially you would go back and up to about here, and you would list, elements 1 to 20 in roughly this arrangement, and each of these boxes above them you would actually draw electron configurations for those individual elements. You may need to have an actual periodic table beside you to call upon the atomic numbers and mass numbers as you require. But that's it for this video.